Hi, my name is Julia Vitale, and this is my Physics 2 Lab 5 presentation, Breaking with Faraday. So the goal of this experiment was three main things. First, to collect real observational data of a magnet falling through a copper tube, then to model the interaction computationally using physics principles, and third, to compare the predicted motion to what actually happened in real life. So experimentally, the magnet took about 13.48 seconds to pass through the tube, that was the average, and then with the computational model, it predicted about 13.14 seconds. So these are the fundamental physics principles that I use in this lab. First is Faraday's law, which says a changing magnetic field through a loop induces a voltage, and then by Lenz's law, the induced current always opposes the change that caused it. And then Biot-Savart law, which tells us the electric currents create magnetic fields around them. And then finally, Newton's second law relates forces to motion, and Newton's third law tells us forces come in equal and opposite pairs. So for this experiment, I held the copper tube vertically and dropped the magnet from the top. And then I recorded the entire fall on my phone so that I could measure the time between when the magnet entered and exited the tube. And then a few assumptions had to be made in order to do the experiment, such as negligible air resistance, that the bar magnet acted as a magnetic dipole, and that the only forces acting on the system were magnetic and gravitational. So this is my experimental data. So over here, these are the physical measurements used in the model. So the tube length was about 1.005 meters with an inner radius of 0.0065 meters. And then the width was 0.001 meters and the outer radius was 0.0075 meters. And then these were the properties of the magnet. And this dipole essentially came from the last lab where we had to calculate the dipole. And then the average experimental fall time was 13.48 seconds. So this is the first part of my computational model, which are the initial conditions. So in the simulation, the magnet will start at rest at the top of the tube, and then the program calculates the changing magnetic field as the magnet moves and determines the induced currents in small rings along the tube. And then the model calculates the magnetic force on the magnet due to those induced currents. So as the magnet moves, the magnetic flux through the tube changes, which induces currents, and then those currents create their own magnetic field that pushes upwards against the falling magnet. So these are the results of my computational model. So using my original dipole moment that I calculated in the last lab, I got a fall time of 3.513 seconds, and then that wasn't close to what I had observed in real life. So by using a smaller dipole moment, I got that the time it took to fall was 1.314 seconds, which is just for 1/10 of the length of the tube. So if you multiply it by 10, you get 13.14 seconds, which is closer to what I actually was able to observe. So now to answer all the questions about interpreting the simulation. So the colored tube in the simulation shows the direction and strength of current in each ring. So by using Lenz's law, I determined that the red represents counterclockwise current and that the blue represents clockwise current. And then if the magnet was flipped, it would still fall this as the same, but the current directions would be flipped. And then the computational model is slightly shorter. And then if I had accounted for air resistance and human errors, then I would be able to improve the accuracy and make it closer to the observed time, which was 13.48 seconds. And then the reason why the velocity versus time plot has that shape is because at the beginning and end of the tube, gravity dominates, but then inside the tube, the magnetic force nearly balances gravity, which creates a very small constant velocity. And then once it exits, it's also, again, the gravitational force would be dominant over the magnetic force. So these are a few sources of errors. So it could be the timing measurement wasn't exact and that the magnet occasionally hit the sides of the tube, which added friction, and then also just ignoring air resistance and uncertainties in the magnetic dipole moment. So if the conductor had nearly zero resistance, the induced current would be much larger, which would produce a stronger opposing magnetic field and slowing the magnet even more. And then if slots or holes were cut into the tube, the circular current loops would basically be disrupted, and then that would weaken the induced magnetic field and the magnet would fall a lot faster. Thank you.